is also Google, which has
Hmm.
up to my knowledge, it has some 53 qubit quantum processor. And
Okay.
then you have China. China
Hmm.
also has, I think, 66 qubit quantum processor. So in India, we, as I said, we have only three labs, and currently like only two labs which are working to perform a scalable quantum processor. Quantum phenomena is like the basic example is the Schrodinger cat example, right? So
Yeah.
like if you have a cat in a box, right, and you have some poison inside that, like in a box, and now
Hmm.
how, if I ask you whether cat is dead or alive, you don't know, right,
Hmm.
unless you open the box. Similar things goes for quantum mechanics. Like you or you can think like there are some people, like bunch of people, and they dance together, right, they dance together, but they will dance together, like if someone is not seeing them, they will stop dancing if someone sees them. So same thing goes for quantum. Like it has a quantum behavior unless you see it. So if you see it, it collapses into the states and you have some observable value. So that's what like is a uh, like
Okay.
basic.
और उज्जवल भाई क्या हाल है? How are you? How the PhD is going? Tell me more about it.
I am good. So my PhD is going good. Currently I am in my fifth year. So mostly it will take one more year to finish my PhD. So before this, I was in ISER Mohali. So
Hmm.
completed by my BS and MS degree in 2018, and
Hmm.
then after that, I joined ISC Bangalore. And currently, I am working on superconducting qubits.
Hmm.
So the goal of my PhD is to like have a four qubit quantum processor. So
Okay.
that will be like a some starting point for India in the quantum computing mission, like
Okay.
in the superconducting qubits technology.
Okay.
Yeah.
And tell me more about how this research goes on and what is the contribution of ISC right now and all about means like apart from ISC where all quantum computers are and what is right now going in India in terms of quantum computers.
Maybe I will go like in the world, maybe just to give you a fair
Okay.
comparison. Like
Okay.
like there are right now many quantum companies. Like IBM is the first, which
Hmm.
currently has like 433 qubit quantum processor, which is like strongest quantum processor we currently have. And after
Hmm.
that, there is also Google, which has
Hmm.
like up to my knowledge, it has some 53 qubit quantum processor. And
Okay.
then you have China. China
Hmm.
also has, I think, 66 qubit quantum processor. We There are only three labs which currently works on superconducting qubits.
Hmm.
So there are many platforms to perform quantum computing. So one of
Hmm.
the platform is superconducting qubits, and
Okay.
there are like many other platforms like trapped ion, like spin. You can use
Hmm.
a spin of a nucleus to perform quantum computation, and then there are many other, like Microsoft is also now investing in
Hmm. Hmm.
technology. They, although they have some different building block for a quantum computer. So in India, we, as I said, we have only three labs, and currently like only two labs which are working to perform a scalable quantum processor. At least some more time in order to have some meaningful quantum processor on which something meaningful can be done. So
Okay.
that's all about India, like
Hmm.
where we are doing.
Okay.
And
And what about ISC? I believe means like one it was your lab. You got some funding of some crores, and there is some another lab. I think Arvind's lab where they were doing the similar stuff.
it was a combined project. So
Okay. Okay. Are
and
you
then
building one or two?
I'm building a four
No,
qubit
means
project.
like okay, 4 qubit
So right
quantum
now
computing. What?
we're working on that. So other
Hmm.
lab has not yet started
Okay.
in a
Okay.
multi-qubit system. They
Okay.
are currently working on a single qubit right now.
Okay.
So
Hmm.
and other than ISC, there is one more lab in TFR. So
Okay.
they
Which
have
TFR?
uh,
Mm,
Mumbai.
okay,
So
Bombay. Okay.
they are doing much better. So they have, I think they have many qubit, like they have performed they have some quantum processor which consists of many qubits, like
Okay.
they work
Okay.
on many qubit system, right now.
Okay.
So in India, we are, I think, if you compare, so I guess there is no comparison, like
Okay.
to
We will be
uh,
less than 25, I think. Whatever. 20, less than 20.
where
What are the maximum number of qubits India has? Maybe less than
right now
20.
there is no quantum processor.
Okay. No
There is
working quantum
where you
computers.
can choose some quantum. So when you say quantum computer, right? So quantum
Hmm.
computer, at least you should have done some. You have done, run some algorithm on that, and you have
Hmm.
got some result. Till my knowledge,
Okay.
there is nothing like that in India.
Okay. Okay. Okay.
Although
And
they,
what about there is
yeah.
this CDAC also in India? CDAC. What's their
So
state of?
feedback right now, like I am working, so my some collaboration is with CDAC also. So for this
Hmm.
superconducting qubits, you need a hardware, right? So we use microwave pulses, and for the
Okay.
microwave pulses, you need signal generators.
Hmm.
So for that, like we have some collaboration with CDEC guys, and they
Hmm.
help us to develop some software and hardware for this quantum computing system. So yeah, we have
Okay.
some collaboration with them. So
Hmm.
yeah, like
Tell me, you mentioned about something related to like sufficiently nobody has performed a particular task on quantum computer. Tell me more about the challenges, how qubit is different from transistor. Means like transistor that everybody know can do computation on a binary level, whereas there is superposition of states on
yeah.
a quantum or a qubit. Tell me more about this.
We'll start with a very basic example. Suppose you have
Hmm.
some maze, like bhul
Hmm.
bhulaiya,
Hmm.
right?
Okay.
So yeah, and if you take and there are many paths. So there is one starting point and there is one end point, right?
Hmm.
And there
Hmm.
are many paths one can take in order to, but there is only one successful path which will take you to the from the starting point to the end point, right?
Hmm.
So
Hmm.
if you take a classical computer, what it will
Hmm.
do, it will suppose there are maybe 20 paths, right? So
Hmm.
what it will do, it will go to one path, it will
Hmm.
see like there is no solution to that, it will come back,
Hmm.
it will go to another path, and then it
Hmm.
will come back. So if there are 20 direction, it will take at least 20 steps to
Hmm.
uh, find the solution to that problem. But if you have quantum computer, right? So in quantum computer you can parallelly execute many directions, right? Like
Hmm.
depending on the number of qubits you have. So
Hmm.
depending on number of qubits in at a particular time, you can search in many different direction, and that will give
Hmm.
you faster result when you compare it to a classical computer. So in that sense,
Okay.
quantum computer is much faster. And one more thing, like I will so if you take a like in classical computer everything consists of bits, like you have 0 and 1, right? So suppose you have two bits, two classical bits, so the combination of that will be 4. Like you can have state like 00 01 10 11, right? If I call, like, it's like a coin, you can have either heads or you can have tail. Like if
Hmm.
you take two coins, then there will be total 4 combinations, right?
Yeah. Full combination. Yeah.
Yeah, but when you take qubits, two qubits, so to any qubits they are currently, let's suppose we take some two superconducting qubits, and
Hmm.
like these qubits, they can have 0 and 1 simultaneously at any time.
Hmm.
So
Hmm.
there also you will have four possible states, like 00
Hmm.
01 10 11,
Hmm.
but they can
Hmm.
also have superposition also. So basically
Okay.
you can encode information in like so when you take classical computer, it will
Hmm.
just give you one output, it will give you 01 or 10 11.
Yes. Yes.
But in
Hmm.
quantum computer you can have like many states in which you can encode information.
Okay.
So
Okay.
if
Okay.
you and these people say it's like exponential growth, like when you use a quantum computer. So why is that?
Because it goes by 2 power something, means
And
like
2 power
2
n,
power
so
something.
like 2
Yeah.
like because if you have two qubits, you have
Hmm.
four possible states, that will be 2 power
Hmm.
2. And now if you
Yeah.
take suppose 100 qubits, your
Yeah.
possible states
It's
will
a
be 2 power 100,
yes.
and
Yes.
that's much larger than number of atoms on the earth. If you
Yes.
calculate
Yes.
the number of atoms on the earth, that will
Hmm.
be like 10 power 50, you will get the answer.
Hmm.
So like that
It means
much
what? It means
information you
what
can
IBM.
create. Yeah,
It
yeah,
means what IBM is doing, like 2 power 400. That much information you can compute on that IBM super
like
quantum computer.
yeah.
That is more than the number of atoms in this universe,
Yes,
I
you
think.
can encode so much information, like And
Hmm.
if you think of doing it with a classical computer, you need many like even the maybe supercomputer can fail in that sense.
Yeah.
So in that sense,
So.
quantum computers are very fast compared to classical
Hmm.
computer. Yeah.
But they are fast related to some sort of computation. A lot of people thinks, like for example, there's Intel processor right now going on, i7, i9, i11. A lot of people thinks quantum computer is just some i100, means like it is like it's like a leap forward in classical computer. However, quantum computer are totally different. It's not necessarily that every task or every computation
Yes.
quantum computer will able to exponentially solve faster. There are some particular kind of task. What you told was a search, majorly search kind of problem, where you have to search in a maze via different directions, I think.
Yes. So this is
Hmm.
called quantum supremacy.
Yeah.
If you have some quantum processor, and if
Hmm.
you can show that some particular problem that can be solved much faster than
Hmm.
that quantum processor compared to
Hmm.
any conventional computer, whether it's supercomputer, then you say
Hmm.
it's quantum supremacy. Like China
Okay.
and Google recently showed the quantum supremacy,
Hmm.
they when compared to the world's fastest supercomputer, so they could
Hmm.
solve the problems much faster compared to those supercomputers. So yeah,
Hmm.
quantum computer, like people believe, but for now, like people have only showed some of the problems which can be solved by a
Hmm.
quantum computer. So yeah.
Hmm.
And you need in order to do everything, you need at least suppose million qubits, and right now you are in a regime where you have only 433 qubits. So there's a long road one
Hmm.
needs to go to
Yeah.
do many more meaningful things. Yeah.
I think it was 2 years back or 3 years back when Google announced they have achieved quantum supremacy. In that, they built a pseudo random number generator. Like generally, all the random number which we generate via MATLAB code or Python code are basically based on some algorithm. Where
Yes.
they have shown, like in 200 seconds, something like that, they 200 second or 20 second, they have produced like random numbers of billions. So they were showing, like in order to generate random number, pseudo random number, if you generate it with via their Google quantum computer versus a supercomputer, so they are saying
Yeah.
we are
So
exponentially very faster. Yeah.
what they did the same thing, and they claim they did it in 200 second, and they
Yes.
claim that a supercomputer will take 200 days. But then IBM came in the way, and they said, oh no,
Yeah.
our supercomputer can do that in just 2.5 days, so why are you
Hmm.
calling it 200 days? So
Yeah.
there is some discrepancy in the definition of quantum supremacy, like
Yeah.
what you called fast or what you called slow, like whether 2.5 days are like
Hmm.
what you will call, like there's some relativeness, right? So
Yeah. Yeah. That
what
is.
is fast, what
So
is
is
slow?
it like can we pose this in terms of, like, this in computer science, the people call it NP hard, N hard, P hard, means like this kind of problem where say according to the lifetime of the universe, they say the time which they give is the lifetime of the universe. Majorly means like any task which takes lifetime of the universe is means like what you are
Yeah,
asking, what is the threshold of the time?
yeah, like there's
Yeah.
no right now standard on the definition of quantum supremacy, right? People, if
Okay.
like they will just solve it, and if they
Hmm.
see like the quantum processor has performed faster, they will claim they have
Okay.
achieved the quantum supremacy.
And there was like some allegations also on that they were working with NASA to generate to build this quantum computer, and it was a project, and they uploaded that paper in on the NASA website, and then they later on, means like in a one month, they have removed that paper from there. I
Yeah,
don't know
there
what
are
was the
many
problem.
debates right now. This was one wormhole they simulated. On that also there were
Oh,
many debates. So
okay.
yeah, so yeah,
Okay. I
and
think
that happened.
IBM, since they are the leader, because they have started so early than anybody else can thought of, and that's why I mean maybe they are like very worried about that.
Their goal right now they have 433. So by 2030 they are saying they will have a 4,000 qubit processor. So uh,
4,000 qubit processor. Okay. Is there
yeah.
any task they are able to do faster, like faster at least than normal
Uh,
classical computers?
Yeah, I think there must be because they have actually commercialized their some of the
Oh,
processors. Yeah, they have
yeah.
actually you anyone can go into the IBM website and they can access and give some job to the quantum computer. And also,
Oh.
like in India, there is no company that is actually using quantum technology, but like outside there are many companies that are actually using the quantum technology in many areas of application. Like there are many companies actually that are doing
And
that.
recently, like US government has passed a law that every inscription based on company like credit card, Visa, Mastercard, and whatever they do, password saving and all, it should be quantum protected. It means since people started using quantum technology, and one of the application or people fear about is like all the encryption will break because it does the things faster, like majorly like factor because it's based on factorization and it can do faster.
So this
Yeah,
was like there was one person Shor's, like
sure.
it's
Yeah.
known as Shor's algorithm, like
Hmm.
where he theoretically he wrote some algorithm where he showed that if you have some very big number, like,
Hmm.
and you can do the prime factorization of that very fast by using a quantum computer, and on that basis only right now our encryption code works. So basically it works on the prime factorization of some very big number. So the
Hmm.
point is the like US is like trying to have some this what do you say, encryption which can't be broken by the quantum computers also, because right now
Hmm.
it's working on the prime factorization. And if now in future if someone has access to quantum computer, they can easily hack that
Hmm.
information. So that's why they
Yeah.
are working into develop more
Hmm.
encryption protocol so that can be
Hmm.
quantum resistant. So
Okay.
the quantum, even there was US actually had one competition where they asked to have some like different algorithm which can't be broken by uh,
Oh,
quantum computer also. Yeah. So
nice.
they actually found one to two algorithm actually
Hmm.
that quantum computer can even take many days to break that. So yeah, there.
Oh,
Yeah.
nice. And what about means like since you talked about different kind of industries like IBM, Google, what other industries are there and what kind of qubit they make? Like
Sure.
you are
So
working on superconducting qubit, and what else other people work on?
shows right now, like if you think of IBM, so IBM is currently working on superconducting qubits. So when you say 433 qubits, that means on one small silicon wafer they have some 433 qubit layout, and they are all made up of superconducting material which can be either aluminum or tantalum, like that.
So that
Similarly,
bigger machine which they have, like which just show this much big, it's
no
like
no
that superconducting
no
part.
no no no,
No.
actually, like in our home we have fridges. So what is the
Yeah.
work of the fridge? So work of the fridge is to like
Cool.
yeah, cool the things, like so that
Hmm.
they does not get bad. Similarly for
Hmm.
superconducting
Hmm.
qubits have some critical temperature. So
Oh.
like if I ask you like do you know anything, like MRI machine?
Yes. Yes. Yes.
MRI machine has superconducting coils inside that.
Oh. Oh. Okay.
That big thing, like when you go for
Yes.
MRI,
Yes. Where people go
some very
inside
big
and
wheel type thing.
yeah.
You know
Yeah.
what is
Yeah.
so there are actually in like this MRI machine, the magnetic
Hmm.
field you get is around 1.5 Tesla. You know, up to
Hmm.
that. And that much magnetic field you can't produce by just using a normal wire.
Oh.
Because because every wire has some resistance, right? And in order to get a very high magnetic field, you need to pass
Hmm.
a very large current, right? Because
Oh.
magnetic field is proportional to the current, and every wire has
Hmm.
some resistance. So if you try
Hmm.
to uh, like uh, uh, produce a very large magnetic field, due to joule
Hmm.
heating, your wire will not survive, it will just get burned.
Oh. Melt. Yeah.
So that's why you
Hmm.
need a superconducting wire, because they don't have any resistance. But when you
Okay.
say they don't have any resistance, that means you are cooling them down below the critical temperature of that. So the
Hmm.
material which is used in MRI is like NBTI, niobium titanium, which has a
Okay.
critical temperature of 15 Kelvin. So now
Oh.
you can ask like how they are lowering the temperature less than 15 Kelvin. So they have some liquid helium inside. So those big
Okay.
wheels, they have some liquid helium inside. That is
Hmm.
basically cooling the NBTI rings to less than
Hmm.
50 Kelvin. so that they can
Hmm.
become superconducting. So
And those, it means those IBM, that entire infrastructure is also.
right now, if I am working on qubits, I have to
Hmm.
first cool down my qubits at least less than a temperature of like 100 millikelvin, less than. So my all experiments I have to do at around 10 millikelvin. So for that, we have one fridge which is called dilution refrigerator that
Hmm.
can maintain a temperature of like 10 millikelvin up to like
Hmm.
many, maybe months and days, depending on
Hmm.
like for how much time you want to do the measurements. So the
Okay.
that big machine you see, that is just
Hmm.
to maintain the
Cool.
temperature of 10 millikelvin. Now you can ask
Oh.
why you need a temperature like in millikelvin, right?
Hmm.
So
Hmm.
these qubits, like they are in of some micron range, like typically they
Hmm.
are around some few micron size, right?
Okay.
And these are like some artificial atoms, natural atoms, like there are some natural atoms, and
Okay.
there are many quantum companies which are using trapped
Okay.
ions as a building block for quantum computer. Similarly, there are many building blocks, right? But when you say superconducting qubits, first of all you need to cool them down. And you need to cool them down. Why? Because these are like artificial atoms, right? So when you say artificial atoms, so they have some energy levels, right? So what we use, so we say, so qubit has two states, right? You need to have two states, 0 and 1.
Yes.
So when qubit is in ground state, we call it 0, and
Hmm.
when we excite that qubit, we call it 1. And that transition energy is typically of, right, gigahertz, like 6 gigahertz, you
Okay.
can say. Now,
Okay.
in order to do anything quantum, first you need to cool it down to a ground state, right? Because if it has some thermal energy, then atom may excite, like it
Yes.
initially it may be in excited state. So
Yes. Yes.
the thermal energy is kbt, which is called
Yes.
Boltzmann constant time temperature.
Hmm.
And if you
Hmm.
have an atom of h bar, some energy omega, then that
Hmm.
quantized energy is h bar omega.
Hmm.
So, in order to bring that system in ground state, your
Hmm.
QBT should be less than h bar omega. And if you
Yes. Yes. Yes.
calculate that for some gigahertz frequency, you will find that your temperature at least has to be in millikelvin in order to actually make them in ground state. That's why,
Hmm.
like IBM, that has very big fridge, right? So, and then your chip is just like this. So that fridge, that whole thing is just to maintain the temperature of 10 millikelvin. Your actual quantum computing chip is just like you can pick it in a hand like this. So
Okay.
yeah,
What about so this is superconduct. Every like what Microsoft uses, what IBM uses, what
no,
Google uses,
different
all of them
different.
are
No, no, no.
superconducting.
So right now, Google and IBM, they are using superconducting qubits, which is called transmon qubit. So
Okay,
they,
transfer.
so in superconducting qubits also there are many type of qubits. Like there are transmon qubits, then you have fluxonium qubits. Like there are a variety of qubits, and each
Hmm.
qubit has its own advantage and disadvantage. But
Hmm.
currently, the transmon is the most favorite qubit of the
Hmm.
like these companies. So right now,
Okay.
Google and IBM, they both use superconducting qubits. Then you have other one company is there, IonQ, that uses
I,
trapped ion as a building block for quantum computer.
trapped
Then you,
ion means phosphorus trapped ion. Which trap?
yeah,
Yeah.
you can. So basically, they take some atom, they ionize that, and then they interact it with the electric field. So they can use strontium, beryllium, and magnesium like that. So currently, and ytterbium also they use. So they first ionize
Okay.
that and they use as a building block. And similarly,
Hmm.
you can have some topological qubits. So Microsoft currently works on topological qubits, which are little complex. So like there are many companies which use different platforms to
Okay.
and each has its own advantage and disadvantage. So if I think of superconducting qubits, superconducting qubits are easy to control, but they are
Hmm.
very sensitive to environmental noise. So they can easily be like collapsed, like they are very sensitive to some noise. Similarly, you
Okay.
have trapped ion. Those are very isolated from the environment, but they are hard to control. So each each type of qubit has its own advantage and disadvantage, and different companies have their own
Hmm.
building block for a quantum computer. So
But the fundamental remains the same. Means in order to build any qubit, you have to bring that isolation of you have to bring those superposition of state between
yes,
0 and 1.
you need to,
So
you can't write like you can't have isolated like you want to couple them actually because you want to
yes.
make some entangled state. So they need to be closer apart so that they can
Hmm.
interact. If they don't interact,
Okay.
then it's just like a single qubit. You have many bunch of
Okay.
single qubit.
Apart from the one single qubit, if there are multiple qubits, there should be entanglement
It can
between
form
them.
many
So what
states.
is that? Is there any particular distance for entanglement, or means like how what
Like
factors
this
entanglement depends on?
key action, entanglement. Like like
Okay.
people are trying to build the entanglement protocol. Like if you are in Australia, I'm in India, and if I can have entanglement, like yeah, like entanglement, if you have one coin and like you are in Purdue, you have one coin and I have one coin, and these two
Hmm.
coins are entangled, right?
Hmm.
So if you have head, I can know here is a tail. Like it has to be a tail. So this is like
It means
entanglement.
our information is coupled in a particular way. If I got some result, it
I will
depends
know.
on yeah,
I
you
will
will
know
know in some or
my result is
so
fixed then.
it's not half probability exactly. If for example like
So,
the
like
probability hampers.
no, it's fixed. It's if you get heads and my heads and two coins are entangled, like
Hmm.
like states are head plus tail tail. So if you got
Okay.
head, then I will get head only. That is fixed. That only
Okay.
you
Okay.
call
Okay.
entangled state. So
Okay.
people are
Okay. Okay.
working on this to use this for quantum encryption, because if you have some entangleness, then anyone in between can't hack, because if they try to do something with it, you will know because you will get the result.
Oh,
So
okay. Okay.
that's why.
Okay.
So people right now, there was one lab in Switzerland maybe. So they
Hmm.
showed the quantum entanglement over 30 meters. So people are
Hmm.
trying to improve that distance so that it can
Okay.
help you in quantum communication also, right?
Hmm.
Yeah,
So that I think sometime back I was hearing this from China also. Military build a quantum communication channel for certain meter. DRDO also after that,
100
like
kilometer.
since there was rivalry, they like they
100
come up with 60 meters, something like that. Like
DRDO did
DR.
100 kilometers.
Oh, 100 meter. Okay, okay,
100
okay.
kilometer. Over
Okay,
100
100
kilometers.
kilometer. Okay,
It showed
okay,
quantum communication.
okay, okay. It means
Like, yeah.
safe. They are building safe in
Yes,
terms
and you
of.
can
Okay,
improve the distance so that
okay.
even in the other countries also you can have that.
Hmm.
Like it's very
Okay.
it becomes difficult to hack, right?
Hmm.
You want to,
Okay. Okay, okay. So it's hacking protection from of military. Okay.
and
So
yeah,
other
like you
things are there,
mentioned
for
one
example. Yeah, you
entanglement.
were
So
saying.
there's no distance. People want to increase that distance. That will be
Okay.
helpful. Yeah.
Okay. What about, let's go back for the basics. How quantum physics, fundamental of quantum physics and quantum mechanics lead to a development of quantum mechanics? There are some phenomena like superposition, entanglement, coherence, decoherence, interference. They are like a bit complex, and how these phenomena leads to quantum computing is still it's like confusing for a lot of people.
So like quantum phenomena is like the basic example is the Schrodinger cat example, right? So
Yeah.
like if you have a cat in a box, right? And you have some poison inside that, like in a box. And now,
Mm,
how if I ask you whether cat is dead or alive, you don't know, right?
mm,
Unless you open the box. Similar things goes for quantum mechanics. Like you, or you can think like there are some people, like bunch of people, and they dance together, right? They dance together, but they will dance together, like if someone is not seeing them, they will stop dancing if someone sees them. So same thing goes for quantum. Like it has a quantum behavior unless you see it. So if you see it, it collapses into the states and you have some observable value. So that's what like is a like
okay.
basic, right? So it's like a state where both states are correlated, like
Hmm,
my head and other your coin head, and similarly
hmm,
the tail. So now if you go to the moon or anywhere else, and if you know you get the head, I will also get the head. So this is like an entanglement. Like you have
okay.
entangled both of them, and you can know what is the outcome of that if you know the outcome of other. So this
Okay.
is like a
Okay.
entanglement. And
So
yeah.
in qubit also that happens, means like the
Yeah,
outcome of
like
one
you
depends on
can
another
create
one.
superposition state very easily. Like
Okay, okay. So, but the fundamental thing is this information propagation means like it's difficult to understand like how information is propagated between two uh, individual which are where they are entangled. What is the information, how information processes between them? Is it like
Like
speed of light or
like
something like
information is same, like the like same information which you encode in a classical computer. It's just
okay,
you have like in parallel you can have many computation steps. Like
okay,
your encoding is same as you do in a classical computer. It's just
okay,
that the computation is much faster when you use
okay.
superconducting qubits.
No, no, my question was entanglement. For example, two electrons are entangled,
Yes.
means like is entanglement a natural physical theory, or it's like how, what is the reason of information exchange between them? Is it like naturally it's a theory that happens, or the information travels via speed of light and it tells other electron, okay, I am head, so you have to be head because we both are coupled?
Yeah, it's a good question.
Yeah, that means like how is it a natural theory? Okay, entanglement happens more, it's like it happens, there is no information exchange as such. So generally whenever we talk about information exchange, we talk about speed of light, means
Like
like information
it's like like there's a correlation. Like you have
it means
correlated.
it's a part of one system only, but you have bifurcated it so that
Yes, it's like
it
a
acts as one system only.
yes, it's
Okay,
access one system only, but they are
okay, okay.
separated in space and time. It's like that.
Okay, 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 okay. So that's there is something like that is like you build the quantum computer. We are right now at the qubit state. For example, what happens? For example, we give a task. For example, you take maze solving task. How we extract out the information? But you have mentioned like if we interact with the qubit, if we interact with the quantum system to observe it, so it
So
will collapse, it will
in,
come back to conventional state. But in order to, so if we are, but qubit we have isolated it, how we interact with it, means like because interaction will cause some issues like
yeah, so one thing like here you so if you take a superconducting qubits, right? So
hmm,
superconducting qubits, one is you control them and then you do the readout. You want to know in which state they are, right?
yeah,
So what
yeah,
happens for every building block, there is a different readout scheme. So what we do in
oh,
our lab, we don't read out qubits directly, but
hmm,
we have one other element which we call resonator, which is like a
okay,
harmonic oscillator, and we couple that to a particular individual qubit, and we indirectly measure the qubit just by measuring that resonator. So directly we are
oh.
not interacting with the qubit,
So
so
if you interact with the qubit, then
it will
it's not a
collapse.
quantum, okay, it will
It
collapse,
collapse
okay.
in that. If you try to
So you
measure it
have to measure it indirectly by some other
indirectly,
ways.
right, right.
So that is called quantum algorithm or something like that, or
No, quantum
uh,
algorithms are like in classical computer you have logic gates like NAND gate,
uh,
AND gate.
okay,
Similarly,
hmm,
when you say a quantum algorithm,
hmm.
it is a set of quantum gates. Like
Okay, okay,
in
okay,
order to do some prime factorization which Shor's give, it uses
hmm,
some particular type of quantum algorithm which is called CNOT
okay,
gate, and one is
hmm.
called Hadamard gate, which is like you can, if you have ground state, you can create the superposition state.
Okay,
So
okay,
it's a
okay,
set of particular gates when you
hmm.
say a quantum algorithm. And we
Okay, okay,
don't directly measure the qubits, we indirectly
okay,
measure them by using some
okay,
other
okay,
superconducting system.
okay. And yeah, means like there was some scientists in 1993 I was watching on video. They were mentioning like it's on impossible to build quantum computers because you have to interact with the system in order to observe something like what you do in transistor. But later on, there is this QEC, quantum error correction. Tell me more about it. What is quantum
So,
error correction and how it
you know,
developed?
so uh, when you have a single qubit, right,
Hmm.
single qubit, you
Hmm.
call it single qubit gates. So basically what you can think a state of a qubit is like a sphere. So where you ground state is a south pole and your excited state is the north pole. And now depending, it's like a rotation. Like if you give some microwave pulse, you can
Hmm.
achieve any state on this sphere. So if you,
Infinite.
yeah, you
Yeah.
can take any state, and if you project
Hmm.
you put it on the equator, that will be superposition state 0 plus 1, because your 0 is on
Okay. Okay.
south pole and your uh, 1 is on north pole, and if you put it on equator, that will be a superposition
Equator
state.
means 2D or 1D where you are projecting. It's a 1D because it's a yours.
It can have different phase,
Oh,
like
okay.
Yeah,
On the equator. Got it.
on
Okay.
the equator. Yeah. So
Okay. Okay.
like like when you say quantum gates, right, it's just a
Hmm.
set of some rotations which you are doing on the qubit. So basically, if
Hmm.
you rotate it by 90-degree, you are creating a
Hmm.
superposition state. If you rotate
Hmm.
it by 180-degree, you are creating the excited state. So this is called single qubit gates. But when you
Hmm.
combine the two qubits, then you need to
Hmm.
do a two qubit gates.
Hmm.
So the problem is, like right now, the superconducting qubits are noisy. So basically, if suppose 100 times you do some two qubit gate rotation, like
Hmm.
right now you can perfectly make them in that state. It's like just 99%. Like there
Hmm.
is some error in that. And when you
Hmm.
combine many qubits, this error actually grows up, right?
Multiplies. Means
Yeah,
like
it actually
multiplicative.
grows up.
Okay.
Basically, you are
Okay.
degrading your quantum system. So in
Okay.
order to make the qubit error free, you
Hmm.
actually need many more qubits, and this is what a quantum error correction called. So in order to
Okay.
make one logical qubit, which
Hmm.
I'm logical mean error free qubit, you need to have
Hmm.
many physical qubit to make them error free. That's why
Is
it's
it?
a hard challenge. It's a
So when
hard.
you talk about 4 qubit, they are physically more qubits.
So see, when you are scaling, na, so error,
Hmm.
if you have some error in a two qubit gate, like when you combine
Hmm.
two qubit and there is some error in that rotation, suppose you want
Hmm.
to take it to excited state, but it has some error, it will not go to excited state. When you
Hmm.
combine all of these qubits, like if you want to scale them, then this error
Hmm.
will be greater, much larger, because it will add up, right? It will add up,
Hmm.
error
Hmm.
will add up. So
Okay.
basically, when
Okay.
you are taking a 4 qubit, your error may not be that much, but when you are taking a 100 qubit, you may have very large error, and you may not able to do
Okay.
anything meaningful with that system.
Okay.
So
Okay.
for that,
It means
people are
it is possible like you have 100 qubits, but resultant is 0 qubit. Means like so much error is there.
yeah, you yeah,
Okay.
you can. So that's
Okay.
why you
Okay.
you need quantum error correction. Quantum error correction
Okay.
means you want to make the qubits error free, and in order to
Hmm.
make them error free, you need to know where is the error is occurring, right? And you can't measure the qubit directly, right?
Hmm.
So what
Yes.
people do, people use many other physical qubits, many other
Hmm.
qubits, and they indirectly measure those physical qubits, and they know where
Hmm.
the error has occurred, and then they try
Oh.
to make them error free.
Hmm.
And that's why in order to make even a meaningful 1000 qubit processor, you may need at least like 4000 qubit or 5000 qubit, although your logical qubit are like 1000 qubits only. So
Hmm.
that is one of the challenge. So
Do you
because
think there will be progress towards this more better quantum error correction code in future? Because
yeah,
what are
yeah,
the I wanted to ask, where are
yeah.
the loopholes with technological advancements those can be take cater? Means like what are those loopholes right now?
I could not hear, can you repeat again?
I'm saying, for example, there are multiple loopholes. One you mentioned about, okay, there are
One
some
is
problem
it's
related
called
to the
decoherence. Decoherence. This is called
okay,
decoherence because your qubit is interacting somehow with the environment, and then
okay,
it's being like it's losing its coherence. So
okay,
that's why these gates are not completely perfect. They have some error. So
okay, okay.
yeah,
So my question was, there are different stages where there can be possibility of future advancement. One is like to cool much lower. Okay, there could be one thing. To
like
have better materials, to have better quantum error correction codes.
yes. So, in I think last year only Google actually demonstrated this quantum error correction. Similarly, there are actually, I guess, few groups only which has
Hmm.
those who have demonstrated quantum error correction on a small scale
Oh,
processor. So one
okay,
is
okay.
in Zurich, and other is
Hmm.
Google, which I know. So they have
Okay.
shown like if you use many physical qubits, and then
Hmm.
you can like you have some logical qubits, but if you use
Hmm.
many more physical qubits, you can
Hmm.
actually make them error free, and they showed that
Okay.
they actually reduce the
Okay.
error.
Hmm.
So
Hmm.
this
Hmm.
is
Hmm.
one of the problem. That's why this trapped ion quantum computer, so they are not very sensitive to environment, but they are very
Hmm.
hard to control. So there is a trade off,
Yes.
so
Yes.
like superconducting qubits are easy to control because these
Hmm.
are artificial atoms, right? So
Hmm. Hmm.
artificial
Hmm.
atoms, you can design them at some different frequencies, at
Hmm.
different
Hmm. Hmm.
like at which you are controlling them. But when you
Hmm.
have trapped ion, those are natural atoms, right? natural,
Hmm.
like they are not man-made. They have some
Hmm.
particular frequency, and it may become difficult to control because they may lead to crosstalk, like you want to excite this but the
Hmm.
other qubit is getting excited, because these are
Okay.
natural atoms. So in that sense, superconducting qubits are much better because they give you freedom to control them individually, but they are
Hmm.
very fragile, like they interact too much with the environment. Similarly,
Okay. Okay.
I was doing experimental on one thing. So what happens, applying magnetic field, you can tune the frequency of the qubits. If you apply magnetic field, you can tune the frequency. And one of the qubit which I made was having a magnetic field at which its tune was about nanotesla. Now you can think
Okay.
earth magnetic field is microtesla.
Hmm.
So if you are keeping it, it may be rotating by, like, it may be fluctuating, right? But
Hmm.
then
Hmm.
how I am making it isolated so that I can apply nanotesla field?
Okay.
So
Okay.
then you need
These
to
are
keep
the.
it in some magnetic shield, because superconductor doesn't like magnetic field. They are diamagnetic, so they
Hmm.
doesn't allow magnetic field from the inside. So
Hmm.
then there are
Okay.
many things which one need to take care of in order to
Hmm.
make this qubit isolated from the environment.
Hmm.
So
Hmm.
yeah.
Hmm.
So you have to be very careful, like when you are doing experiments with the superconducting qubits, because they are very sensitive to the environmental noise. Yeah.
Okay.
So this is one
What
of the,
about?
yeah,
Yes.
yeah, tell.
Yeah. Continue. Continue.
No, no, then tell.
Okay, so what I was asking, there are multiple applications of quantum computer.
Yeah.
Some of them are saying quantum encryption. Okay, quantum encryption will be much more,
So
can't be broken. There is a drug discovery. Okay,
yes,
they are
yes,
different
yes.
kind of majorly those kind of problem which are right now optimization problem. Right now we solve optimization problem using some algorithm and using deploying it on transistor. And you said it correctly, exploring different parts one by one, it's more taking time taking than exploring all of them together. And you should have,
Parallel, you can have,
pal
yeah.
yes, yes, yes. So what all application could be there in future for quantum
So
computing?
like this, I just hear like it can have defense. In defense, it can have much
Hmm.
application, like which I have here. Like US already using quantum computer for defense. So like it's very
Okay.
powerful. Like you want to track some missile or like that, so they are really
Okay.
powerful. And
Okay.
suppose you have two paths and you want
Hmm.
to know the shortest path between them, so this is
Hmm.
one of the application. So there
Hmm.
are variety of applications, like I
Okay.
think
All the
if,
all the optimization problems can be directly converted to, like, can be directly deployed onto quantum
yes,
computing.
yes, because
Okay.
you have many states to encode information, right? As I
Hmm.
told you, you have, if you have 100 qubit, you have 2 into 10 power 100 states.
100
Yeah,
state means
because
like that much you can compute on. Okay.
yes, yeah,
Okay.
that much, like
And
you can do faster, like when you have
okay.
much larger qubit
Uh,
system.
Okay, so remember last time when there was COVID, and we were at home, and that time everybody was waiting for the first vaccine to come. A lot of people were doing, their computation of drug discovery, COVID drug discovery on supercomputers. But at that time, a lot of people were saying if there would be a quantum computer, it
Yes,
would be like within minutes and or within days instead of waiting for a year or so. You know,
yes. Yeah, it
that's
like
true.
it has lot of application, like
Hmm.
this quantum technology has actually revolutionized. Like if I think, I can tell you, like one is this MRI, this, it's a quantum
Hmm.
phenomena, because superconductivity is there. Superconductivity is a quantum phenomenon. Similarly, this LED TV, which uses quantum dots. So
Hmm.
quantum dots are
Hmm.
nanometer size nanocrystal, which
Hmm.
emit different colors depending on their size, and they are
Hmm.
used in, like Samsung is already using them in their TVs.
Hmm.
So there are
Hmm.
many things which right now uh, quantum technology, which are using quantum technology. And once
Okay.
you have a quantum computer, I think we can do much more than we are thinking now. Like there can be
Okay.
lot. Yeah.
That's true. That's true. And apart from that, I want to discuss about little more about, like, US is very far away from any possible country. The country which may come near to them, I think maybe UK or some Europe or China.
China.
So what is our contribution where we are doing? Like recently I heard this
So
6,000 crore.
like when you see in US now, like there are a lot of people which is working on these things. Like
Hmm.
there's a, I may not know, maybe 200, 300, 400 people which are currently in my lab. There are 3 person which are, so you can think it's a manpower. One thing, it's
Yeah.
manpower. You don't
Investment.
so much trained professionals which are
Hmm.
doing research in India. So if you have
Hmm.
two labs, like, and you have just 10 people, like it's become really hard, to do that. And when you in outside, like in US, you have like many groups which are currently working on superconducting qubits. Like I think they are
But do
20,
you
30.
think it's India has sufficient trained people? But means like you can train people. Do you have such investment to build tens of lab and give them 20 crore, 30 crore rupees or not?
But you don't have like uh, those scientists, like if I think, uh,
Okay, supervisors. You mean to say
yeah, you can say that you don't have
scientist?
many, like, or what should I say, like there are no manpower, I will say. Like
Okay, okay,
even
manpower.
if you
Okay,
give the money, like it may not be successful. It may not.
okay, okay. So
So,
you mean to say we have sufficient amount of money? Recently, government of India announced this 6,000 crore for how many qubits they want to build in 8 years?
so they are saying 100,
100 qubits. Okay, 100 qubits
100 or 1000,
in
100 or 1000
okay,
till 2030.
okay.
So
1,000. How it is possible to beat
in
IBM?
2017, this was one, actually there was first this
Hmm.
QUST program, QUST, where they
Hmm.
first time passed some budget about the quantum, right?
Hmm.
Some 800 crores, I guess. They,
Hmm.
and that time they said by 2022 we'll have a 4 qubit system, but we don't have it right now, right? And it was
Okay, you will make it maybe in 6 months.
maybe, for sure, I will try. I'm trying, but
Okay,
like
play less cricket, focus on work.
yes, doing that. So the point is, like, although they have passed some project, but it's good if they get the, like, whatever they aim for. But
Hmm.
yeah, the point is, like, it will take some time for India in order to revolutionize or do
Hmm.
something in the field of quantum, or having enough application related to the quantum technology. So
Because like people trained like you, definitely if you want to do something about that you have to go outside India, and then outside India if you go there are so much salaries in quantum computing or quantum related stuff, then people
yeah,
avoid, means like it's very difficult to come back to India to.
actually, if I can tell you, like there are so many companies right now which are using actually quantum technology. They are based on quantum. Like there are many startups outside, not in India, but there are
Hmm.
many startups, and they actually use quantum computing or quantum computer for many applications. Like lot of
Hmm.
applications, they have different companies. So
Hmm.
yeah, for sure, people, if they go, like if in India I suppose I made 4 qubit processor, what I will
Hmm.
do here, you tell me. Like I don't
That's
have,
true.
I will need to go outside, because I see there is a like work which is based on my work. So
Yeah,
for
you
sure I
have to
will.
progress in your career also, you know.
Yes, like,
Yeah.
or at least there should be something, or maybe someone
Hmm.
has to do some startup so
Hmm.
that it can form. But something, someone has to take the initiative, right? Someone has to
Hmm.
do, like,
Hmm.
someone has to start some company or anything that
Hmm.
is related to quantum, but is not that.
Okay,
I
got it.
can tell you one story. So this there are many companies. So Europe is also like uh, doing some quantum. So uh, if you want to have a, like, maybe 20 qubit processor system, so
Hmm.
what do you think if you want to import it from some outside? Suppose you are in Purdue, right? You want
Hmm.
to suppose have some maybe 20 qubit processor, but you don't have
Hmm.
it. But
Hmm.
US can give you. So
Hmm.
how much money you think it will cost to have just a 10 or 20 qubit processor?
I don't know. Means like since I am in US, I don't know. Means like
150
maybe
crores,
150 crore for how much? 10 qubit.
like that, some small scale processor,
It's
right?
the see that happens in everything. Any new technology, since it's like a monopoly, so you can ask anyone because there is a research investment also that happens even in aerospace and defense. If we buy costly like F-35 and something like that, it's difficult to get it because they are very costly.
Like in India, like you can
Hmm.
have quantum computer from outside also, right? India
Hmm.
can ask for, but it's a good thing that they are not doing that thing, but they have
Hmm.
raised their own budget.
Hmm.
Like they
To
want to
build.
invest their own money, they don't want to import it, so that's a good thing. Like
Okay.
other
Okay.
countries, they can import it from anywhere, right? But it will
Hmm.
cost a lot of money. Like you can
Hmm.
think, If you want to
Yes.
have a many qubit system, I think it will be like 1,000 crores, like that.
Hmm.
So that is too much money.
And apart from that, there are challenges related to, then you have to, like, for maintenance and all these issues and all, you have to call them again and again. It's not only one time charges, you have to like
There is
keep
no
them in the
maintenance.
loop.
There is no
Yeah.
maintenance actually.
Yeah.
Once you have a working qubit device,
Hmm.
so it's just the refrigerator.
Maintenance of the entire system, maybe, is it
There is no
possible?
maintenance. Like
Oh,
maintenance means you need to calibrate your gates. That is one
okay.
thing. There's
Hmm.
no, I think there's no maintenance. Your
Okay.
maintenance will be only be doing on the fridge, which you are using to cool down the things. That you may
Okay.
not run longer, like,
Hmm.
because uh, yeah, that can only be the issue. But yeah,
Okay. Okay.
once you buy it, you can run it for years.
Hmm. 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 Okay, so we were talking about this deco decoherence thing. Can
Yes.
you explain it more? Means like,
So
what is
yeah,
error? What is error? A lot of people, every time you hear about error,
so I will
error
tell you
correction.
error versus decoherence. Maybe that is a
Okay,
good.
okay,
Okay. So
yeah.
when you say error, suppose you take a single qubit, right?
Hmm.
So I
Hmm.
told you single qubit states can be laid out on a sphere. So when
Yes.
it's in ground, it's on the south pole,
Hmm.
and when
Hmm.
it's excited, you are in the north pole, right?
Hmm.
So what happens?
Hmm.
Suppose, and what you are doing basically, it's like what you do on magnetic resonance imaging. You basically give some microwave pulse of
Hmm.
that particular time so that it
Frequency.
can take to this excited state.
You
Now,
mean to say for every possible state, there is a possible frequency
no,
which will cause
so,
it to go?
no, I told you na, these are artificial atoms and they have
Hmm.
some quantized levels which are
Okay.
not equidistant. So what
Okay.
we use just two levels, two closest levels. So the transition frequency of that is gigahertz.
Okay.
So
Okay.
now
Okay. I
I
got
am
it.
saying the ground state is North Pole and the first excited state,
Okay.
ground state is South Pole and the first
Hmm.
excited state is North Pole.
Hmm.
And
Hmm.
now you need to give some gigahertz pulse because the
Hmm.
frequency is gigahertz. And if you give this gigahertz pulse, you can go to the North Pole. So
Hmm.
now your if your this pulse is not very well calibrated, you may end
Hmm.
up at some angle from the
Hmm.
this excited state, and that is a
Hmm.
type of a error. You will
Hmm.
call it
Hmm.
error because it will
Hmm.
keep accumulating. Like suppose you want
Okay.
to do a series of gates, this error
Hmm.
will keep accumulating every time.
Ah, I got it. Yeah,
It
in
will, like,
multiplication.
if you are doing some computation, it will not run for longer time because
Hmm.
it will collapse because
Okay.
after
Okay.
every time your error will take over.
Hmm.
Now, when you come to decoherence, right? So, decoherence is suppose you have some atom. Let's say
Hmm.
you have some artificial atom. So, when you excite it, right? When you excite it, so every atom, if it goes into the excited state, it will come to ground state. This is called spontaneous emission. This is called spontaneous decay or emission.
Hmm.
So, this is called a decoherence. Basically, at what rate your atom is decaying. This is a one
Hmm.
type of decoherence. So,
Okay. Okay.
so
I got it. I got it.
So
Do
this
you
is
know
a
recent?
yeah.
Yes. Yes. You were saying about
So this is just
decoherence.
a difference between decoherence and error. Like decoherence is basically your system is interacting with the environment and it's decaying to its
Oh.
ground state. So
Okay.
now
Okay.
you
Okay.
can
Okay.
think, suppose,
Hmm.
and we call it relaxation time. So
Hmm.
relaxation, because suppose you have some qubit which has a
Hmm.
relaxation time of suppose 10 microsecond.
Hmm.
Suppose 10 micro,
Hmm.
and then you have a gate time. Like gate
Hmm.
means how much time it takes for the qubit to go from south pole to north pole.
Hmm.
Suppose that is 50 nanosecond.
Hmm.
Now you can think how much gate you can do
Hmm.
before the qubit decays to ground state. So you will
Okay.
do
Okay.
10 microsecond divided by 10 nanosecond. So that much gates you can apply before your qubit
Hmm.
decays
Hmm.
into
Hmm.
the ground state.
Hmm. Hmm.
That's
Hmm.
why
Hmm.
people want to improve these coherence time, which you call
Hmm.
decoherence. So basically
Hmm.
people want to get rid of this decoherence, or they want to reduce the effect of decoherence, because you can do much larger gates, or you can do much more computation on that before the
Hmm.
qubit decays to ground state.
Okay, okay, I got it. So there are challenges on that also. Where, what about you? Where are you finding most challenging thing for a superconducting qubit? What is the most challenging? What you face and what other researchers may face? Researchers may
uh,
face.
so fab is one of the thing, because
Hmm.
fabrication. So if
Okay.
you can think what this IBM is using, I can tell you like what the IBM is using as a building block. So it's
Hmm.
just type of a LC circuit. So
Hmm.
LC circuit.
Yes. Yes.
take a inductor and a capacitor in
In the
parallel.
inductor and
It's a
yes.
LC circuit. It's like a
Hmm.
harmonic oscillator.
Yes.
And in harmonic oscillator, your levels are equally spaced
Hmm. Hmm.
because your energy is h bar omega between
Hmm.
different levels.
Hmm.
So now what they are doing, if you want to excite just the first level, right? If you want to excite the first level, because your energies are same, you will be climbing the higher ladder also because it's h bar omega. If you give h bar omega, it will go to the higher levels. So what
Hmm.
they are doing, instead of using a linear inductor, they uses
Hmm.
a just a non-linear inductor, which is called Josephson junction.
Okay.
So Josephson effect, if you take a normal metal,
Hmm.
if you take a normal metal and you have some insulator, and then you
Hmm.
have a normal metal.
Hmm.
So sandwich, it's like a sandwich, some metal, insulator, and metal. So
Hmm.
now try to pass some current. What do you
Hmm.
think? Will current flow from here or not? It will
It
not because.
intuitively it doesn't feel like it should pass because there is an insulator between them.
So what happens when you take a superconductor, but and you have some
Hmm.
insulator and you have one
Hmm.
more superconductor,
Hmm.
your dissipation less current flows. This is called
Oh.
Josephson effect. So at
Okay.
quantum, at low temperature, this effect comes.
Okay.
Although you have some insulator,
Hmm.
then also you can have a dissipation less current flowing through that without
Oh.
generating any voltage. So this is called Josephson effect. So
What could
on
be
the
the
basis,
reason for that? What could be the
because
reason for that?
quantum, like from the quantum mechanics, your electron can tunnel from one to other, and
Okay. Okay.
electron is a
Okay.
wave function. Like there
Ha
is a
ha
wave
ha.
function, and when you have this thin insulator in between, your
Hmm.
wave function can overlap on both of the superconductor, and
Got
then
it. Got it.
your electron can tunnel from that to other. So
Okay. Okay. Okay.
superconductor, although you have Cooper pairs, like they
Hmm.
doesn't act as a single electron, but they act
Hmm.
like remains as a bunch of electron, like two electron together. So
Okay.
because the wave function overlaps of these Cooper pairs, so that's
Hmm.
why there is a dissipation less current. Like
Okay.
classically, you can't explain this behavior, right? Because
Hmm.
you will
Hmm.
say it's an insulator, nothing will pass through it.
Yeah.
So
Yeah.
on the basis of this only, these superconducting qubits are built actually. So every
Okay.
superconducting qubits is using this Josephson junction,
Hmm. So there
and
should
that
be a particular thickness of that. More than
yeah,
that,
it's
it is
like
not possible, I think.
3 to 4 nanometer.
Okay. 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 Hmm.
So because
Hmm.
after some time, if you make it very thick, your like wave function may not overlap, and it
Hmm.
may not act like a superconductor. This whole thing,
Hmm.
yeah,
Okay.
that's why.
That's nice. That's nice. So these are the challenges
So
which
challenges
you
is
are.
fab challenge, and as I told you, for single qubit you need microwave generators, right?
Hmm.
So when you are using 100 qubits, you need 100 signal generators. So there is a one
Oh.
challenge in hardwares also. So there is one research which is going in order to compact the hardware. So
Hmm.
where you can like build a more complex system in order to
Hmm.
control these superconducting qubits.
Hmm.
Similarly, as I told you, this chip has to be attached in this fridge, right?
Hmm.
But
Hmm.
this need to be wired to your outside environment, and
Hmm.
if you have 100 qubit, you need so many connections, right? So there is one more research like how to compactify these wires
Hmm.
all together. So there are
Hmm.
many research direction in which people are working on to
Hmm.
make the
Hmm.
things compact. So
Okay.
yeah.
Sometime back recently there was a news. I don't know. Means like it is a continuous news which keeps on coming, and you can see in the Nature paper room temperature superconductivity.
Yes. So
Like what is
why you
this?
need a why you need a room temperature
So
superconductivity
to
first?
remove this all these whatever you are cooling it to, I don't know, means like 4 Kelvin, 3 Kelvin.
If you have room temperature superconductivity, first of
Hmm.
all, as I told you, this MRI example,
Hmm. Hmm. Yeah,
you can
it will be
have
small.
much
Hmm.
larger magnetic field you can produce
Hmm.
without burning the cables because they do. So this is one thing. Second
Okay.
thing is electricity.
Hmm.
You can have like dissipation less electricity if you have superconducting wires, right?
What
Because they
about
don't.
quantum computers?
Quantum computer, it will revolutionize actually. It will
Okay.
revolutionize.
Hmm.
It may revolutionize on because
Hmm.
this Josephson effect may not work at room temperature.
Hmm.
There are
Okay.
like, although there is nothing like room temperature superconductor till now, like
Till now,
and
but like a lot of people claims it. Do you know, remember ISC claimed
no,
it
no,
some like 2019 something like that?
yeah,
Yeah, there is like.
yeah. So there is a lot of research is happening in this area, to
Hmm. Hmm.
try to improve upon the things. so
Hmm.
that can basically ease your life, like.
Hmm.
Yeah.
That's true. That's true. Like we should have more focus, more funding, and more trained people to
Yes,
have these
that's
kind of things.
that's one
Yeah.
thing, yeah, that needs
That
to
is
be
very
done.
important.
Your
And
camera is
let's
gone.
come back to a lot of these things looks artificial, like whatever we are building is human made, like artificial technologies. But on the nature scale also, these things actually nature computes everything. Computation happening on the natural scale, which we see all around on a biological scale, are also quantum computing, I believe.
Yes, one example. Your camera is gone.
Is it? Well, I
Yeah.
think I can see that. It's okay. Means like it will be uploading.
Okay. So
Yeah.
one, this photosynthesis. So
Yeah.
one group in California, I guess, Berkeley.
Yeah.
So
UCB, huh? UC Berkeley,
yeah.
huh?
So they showed like this photosynthesis is actually a quantum computing type thing,
Uh,
because they told like, when you have a leaf, right? So they say whole of the solar energy is falling onto that, but
hmm.
like, where this energy is going, like how this photosynthesis is happening so fast. So
Yeah,
because
in a million and billionth of a second, huge
yes.
amount of energy is converted. Energy is converted from light to carbohydrates so fast. How it is possible? Yeah.
Yeah, so where this photosynthesis is happening, there is some photosynthesizer which is at some particular place in the leaf, right? So energy has to go there, and then the reaction take place, right? So the researchers argued like how this energy, like without dissipating, is reaching so fast there, like how this chemical reaction is happening so fast in like 1 billionth of a second. So they say like when the energy is falling, instead of going in one particular direction, it goes in every direction. It's like a maze example. So basically that's
Yeah.
why you are saying it's like a quantum mechanical effect, like your energy is coming and it's going in every direction. So then they say it's like a quantum computing effect. So yeah, some biophysicist in
Yeah, that paper was published in Nature also. Means like, what else you want to discuss about? Means like quantum computing challenges, and what else is there? Whether it's possible to build. There are some allegations also. Some people say it's just an investment, and it won't
like,
work out.
yeah, like in our lifetime I don't think like it will work.
Okay, in
You
not in like
may,
100 years.
I don't know, like, it
Okay.
may take years actually, much larger than, like when you say, when you like, right now you are building a small scale processor, and you are solving just one particular problem, and you are saying you have achieved quantum supremacy. But in
Hmm.
order to do everything, you need at least a million qubit, error
You mean
free,
generalized computer like what we have
generalize
right now?
everything, like
Oh.
not just a particular problem, but if you
Hmm.
want to generalize, you need large amount of qubits, right?
Hmm.
And that will take, I think, much. You can think like why IBM in 8 years will go from 433 to 4000 qubit, and it
Hmm.
takes a lot of effort, like in order to. So when you are saying 4000 qubit, you just not need to lay the qubits, you need to think about the hardware, you need to think about this fridge, because
Hmm.
this fridge, when you are saying 10 millikelvin, if you put too
Hmm.
much energy on that 10 millikelvin stage, you will
Hmm.
start heating up the system. So you
Hmm.
need to also increase the cooling powers of these machines also. So one
Hmm.
needs to work in every direction in order to get to that 4000 qubit machine. So
Hmm.
in 8 years, if you are moving from 433 to 4000, now you can think like how much time it will take to reach up to maybe 1 lakh also. So
That's true. That's true. Reaching to the similar transistor level, like as you can see, like we
I
have
remember this
billions of
maximum,
transistors.
maximum transistor right now is an M1 chip, Apple, which has 14 billion transistor. Then it's
Yes.
Ryzen chip,
Yeah.
which has
Yeah.
10 billion transistors right now.
They have reached, like right now the technology is around. Apple has, like Apple can build around 2 nanometer, 1 nanometer, like
Oh,
chips.
I
Yeah, I mean
thought
like,
it's
you
like
can
10 nanometer.
1 nanometer, 2 nanometer. When you divided when you divide 1 centimeter by 1 centimeter chip divided by 1 nanometer, so it comes around the number of transistors. Yeah.
Right. So
Yeah,
yeah.
that's true.
So this earlier Moore laws used to happen, like it was, but right now we are
More
not.
law.
It's like a linearly we are growing, and that's where the
Oh.
quantum computer comes, and they are revolutionizing the this computation right now. So we are not
Hmm.
in a Moore's law regime right now. So
Okay.
it's like a linear growth, because you can't make the size very smaller, because then quantum mechanical effect will take over, where the quantum tunneling will happen, and your transistor will not be a transistor then. Right now you are using it as it as a switch between 0 and 1 by controlling the gate voltage. But if you
Hmm.
try to reduce it much smaller, your quantum
Hmm.
mechanical effect will take over, and you can't reduce
Yes.
it much further. So that's
Okay.
the
Okay.
one problem.
Okay. So that are these are fascinating thing. After means like I was trying from so long to have one podcast on quantum computing, quantum mechanics, and thank you for coming to the podcast.
It was also my first like such type of interaction. So
Okay. Thank you for this podcast, amazing podcast. And
thanks to you for asking me to be on this podcast.